Understanding that there are forces of attraction between separate molecules helps us explain how they move through their phases. So from a solid to a liquid and a liquid to a gas. So we're going to take a closer look at this phase change process. Solids have the highest interaction between the separate molecules. They have the lowest amount of energy, or what's called kinetic energy. So kinetic energy is the energy in the movement of particles. Solids have the lowest kinetic energy, and because they have the lowest kinetic energy, they're going to have the highest interaction. So that means that you're going to maximize the amount of intermolecular forces. With this, we can look at the fixed shape and the fixed volume of that solid. It is measurable, right? So it cannot be squished. It's going to have that repeating solid structure like we had talked about with the types of solids. Liquids, we have an increased amount of kinetic energy within that liquid. So you go from this rigid state to this flowing state where they are going to start to move. And depending on the temperature of that liquid, they're going to move faster or they're going to move slower. But because they're moving, we have decreased the permanent interactions between those molecules. So we have weakened those forces enough to allow that lattice structure to break. So we have that definite volume, but not a definite shape. It's going to take the shape of the container in which it's in. Still cannot be squashed because the molecules are still really close together. Whereas a gas, the gas, we have essentially heated it up enough that the kinetic energy has broken any of the intermolecular forces or the forces of attraction between the separate molecules. So now they are moving around. They have no or negligible forces. The only time they have a force is if when for the little bit of time they interact with each other's or the surface of the container. All right, so they have no definite shape, no definite volume, just based off the container in which they are in. But with gases, we can compress them, and that's where we talk about our gas laws, pressure, temperature, and volume. And when we do that, we can technically force back into a liquid state if you force those gas molecules closer together, which we'll talk about later. Phase change is the movement from one state to the next. So starting down at the bottom. So in a solid, we have that highest interaction of molecules possible. As we add heat, okay, we're going to add energy, kinetic energy, and we measure that based off temperature. And so as we add that heat, we are going to be interrupting and disrupting the forces between the separate water molecules, and they're going to spread out. And then as we add more heat, we're going to continue to interrupt those intermolecular forces between those substances, essentially breaking them to allow those molecules to break apart into their gaseous state. Because we're having to put in that the energy to increase that kinetic energy, this process of going from a solid to a gaseous state is an endothermic process. We have to put heat into that system. Going from a solid to a liquid, that substance is going through what's the phase change that we coin melting. Going from a liquid to a gas is boiling. There are times when we have enough energy quick enough that a substance can undergo sublimation. And sublimation is the direct transfer from a solid to a gas. So like dry ice. Dry ice has to be cold enough, and there has to actually be enough pressure, so it needs more pressure than the atmosphere provides. So it has to be in a pressurized freezer, cold enough, like about -77 degrees Celsius, will allow CO2 to go into a gaseous state. As soon as you open the lid to that freezer, the pressure has been released and the temperature is we're nowhere near as cold as it needs to be. So it's skipping the liquid phase. It's going straight to that gaseous phase because of the quick input of energy. When we go back, so we can take a gas and we can cool it. And this process is called condensation. So as it condenses, this is like when you have a glass of like iced tea or ice water or whatnot, and you get that condensation on the outside of the glass. So what happens is the atmosphere, the particles in the atmosphere, specifically water, is hitting that colder surface that is the glass, and it's losing kinetic energy, it's losing its heat, and it condenses on the outside. And then eventually we will cool it enough to freeze that liquid into a solid to create that ice. Because these molecules are slowing down, they have to give off that kinetic energy to increase their forces of attraction. So this is an exothermic process. It is giving off heat. So this is a reason why you can get something called freeze or burn, because enough energy has to be given off to go from that liquid to the solid state, that energy has to go somewhere. So you can get burned by something that is frozen or going through that freezing process. We can use graphs to help us visualize this transition or these phase changes for different substances. And this will allow us to determine melting points, boiling points, so on and so forth. So with this curve, so we can have heating curves or cooling curves depending on what we're doing. So with these curves, you're going to be measuring temperature versus the heat or energy. So temperature is going to be on our vertical axis. Heat or energy is going to be on the bottom. Really, this is just kind of representing a general flow. So in a heating curve, we're looking at starting with a solid, and we are looking to that transition all the way to the gas. We have to add heat for this process to occur, and we see that increase in temperature. So that is the endothermic process we have been talking about. So what happens is when we are heating, so on this first line, we have our solid water, and we have to add heat to interrupt those molecular forces. So we have the solid, and it's going to slowly start to move. And it's going to get to the point that we call the melting point. And at that melting point, the temperature actually plateaus. The temperature is not going to change in the solution even as we continue to add heat. But the temperature is not going to change because what's happening now is we have interrupted enough of the intermolecular forces. We're starting to see that phase change. And so during that plateau, you are going to increase the motion of the molecules in there, and so all the energy is going to that interruption and that phase change. It's not until the phase change is complete, where all the particles have gone in from the gaseous to the liquid state, that you start to see that temperature increase again. So once all those particles have turned into the liquid state, you're going to see the temperature increase as that liquid starts to heat up. When we plateau again, that is our boiling point. And so this is the transition of our liquid to a gas. And so once we hit that plateau, once again, we are now no longer inputting energy into the liquid, but into breaking those intermolecular forces to allow them to escape from their liquid to their gaseous state. Same concept with cooling curves, just in the opposite direction. So on a cooling curve, we are going from a gas down to the solid, right? So we have to remove that energy. So we're cooling that gas down until it can condense. So we're taking away and reducing the movement, the kinetic energy of those gas particles, and they're going to start to interact with each other. At this plateau, this condensation means we now have less energy. So this is our exothermic process, that we can now start to reform those intermolecular forces. So we're going to start to reform those, and we are going to condense that steam into a liquid. Once all of those gas particles have transitioned from their gas to their liquid state, we will start cooling the water. And so that water is going to cool down, and you get this really cool process, what's called supercooling. And so it will cool so fast and lose all that kinetic energy and come together that it'll actually dip below the freezing point. And what happens is they don't form in their correct lattice structure. It's kind of wompy, kind of like an amorphous solid. And so then they will break just enough, taking enough kinetic energy to realign to form that lattice structure, and that's that freezing point. And then we can cool from there.